High above Antarctica, something extraordinary is unfolding. A stratospheric heat wave of historic scale. Temperatures in the stratosphere, usually around -55 degrees Celsius, have soared to -20, a staggering 35-degree jump. This isn't a minor blip. It's a dramatic, three-pulse warming event since early September, shattering the Antarctic winter's deep freeze. The stratosphere, 12 to 40 kilometers above us, is usually kept cold by darkness and isolating winds. But now it's been jolted by a major atmospheric disturbance. This warming will ripple outward, shifting wind patterns and weather across the southern hemisphere, Australia included. Scientists are watching closely, as this event could signal a season of heat and dryness for southeastern Australia. The frozen stratosphere's sudden warmth is a wake-up call. Even the most remote parts of our planet can change in an instant. To grasp what's happening, let's break down sudden stratospheric warming, or SSW. SSW is a rapid, dramatic heating of the stratosphere, driven not by sunlight but by powerful atmospheric waves rising from the surface. These planetary waves, generated by air flowing over mountains or between land and sea, can surge upward, releasing energy and causing the stratosphere to warm by tens of degrees in days. This sudden warming disrupts the normal winter circulation above the pole, showing how surface events can shake even the highest layers of our atmosphere. The current Antarctic event is a textbook case. Multiple waves have delivered enough energy to spike temperatures by 35 degrees. SSWs aren't just scientific curiosities, they can reshape weather for millions. Understanding SSW is key to predicting its far-reaching impacts, especially in the southern hemisphere. At the core of sudden stratospheric warming, or SSW, lies the stratospheric polar vortex, a vast spinning mass of intensely cold air high above Antarctica. This swirling system is one of the most powerful and mysterious features of our planet's atmosphere, dominating the upper layers during the long polar night. This vortex, encircled by powerful westerly winds, acts as a fortress, locking in the frigid air and stabilizing weather patterns across the entire southern hemisphere. It's like a giant atmospheric barrier, keeping the cold contained and maintaining a delicate balance in the climate system. But when planetary waves, giant ripples in the atmosphere, push upward from below, they can disturb, weaken, or even reverse the vortex's winds, much like tipping a spinning top off its axis. This disruption can have dramatic consequences. The current event shows the vortex has lost its strength, leading to a staggering 35-degree temperature surge in the stratosphere, an extraordinary and rare phenomenon that signals a major atmospheric upheaval. As the vortex breaks down, cold air escapes its boundaries, warm air rushes in, and a chain reaction begins. This sets off a cascade of changes, shifting wind patterns all the way down to the surface and altering the weather we experience. The weakened vortex disrupts the jet stream, steering weather systems in new and unexpected directions, sometimes sending storms and unusual weather far from their typical paths. This is how a stratospheric event, unfolding high above Antarctica, can set the stage for dramatic and far-reaching weather changes far below, even thousands of kilometers away. The fate of the polar vortex is the critical link between the upper atmosphere and our daily weather, connecting distant stratospheric shifts to the conditions we feel on the ground. The polar vortex's disruption starts with planetary waves, giant ripples in the atmosphere, often borne thousands of kilometers from Antarctica. These waves, created by air flowing over mountains or between land and sea, can sometimes travel vertically into the stratosphere during winter. When they reach the vortex, they break, releasing energy that heats the air and slows the vortex's winds. In major events, the vortex can even reverse direction, signaling a total breakdown of polar circulation. The current Antarctic event, with its series of heat pulses, shows sustained, powerful wave activity. This relentless wave assault has dramatically warmed the stratosphere, setting up major shifts in southern hemisphere climate. The process is a vivid reminder of how interconnected our atmosphere is, from the ground to the edge of space. planetary waves are the hidden force behind these dramatic atmospheric upheavals. Sudden stratospheric warmings, or SSWs, occur at both the North and South Poles, but there are some striking differences between the two. SSWs are much more frequent and intense in the Northern Hemisphere, making them a regular feature of Arctic winters. The Arctic's geography is incredibly complex, with vast continents, sprawling oceans, and towering mountain ranges. This landscape generates powerful planetary waves that travel up into the stratosphere, constantly disturbing the polar vortex. As a result, the Arctic vortex is weaker and more likely to break down, leading to dramatic shifts in weather. When an SSW strikes the north, it often sends frigid Arctic air plunging southward, triggering dramatic cold snaps and severe winter storms across North America, Europe, and Asia. These events can disrupt daily life and even impact energy demand. In contrast, the southern hemisphere is dominated by an uninterrupted ring of ocean around Antarctica, with almost no major mountains to disturb the flow. This makes the Antarctic polar vortex colder, stronger, and much more stable than its northern counterpart. Only exceptionally powerful planetary waves can disrupt the Antarctic vortex, which is why major SSWs are so rare in the south. Most years the vortex remains undisturbed, keeping the cold locked in. Even so, when events do weaken the vortex, like the rare SSWs in 2002, 2019, and now, they can have huge impacts on southern weather patterns, even if the winds don't fully reverse as they often do in the north. Understanding these differences between the poles is crucial for forecasting extreme weather in places like Australia, New Zealand, and even South America, where Antarctic air can sometimes reach. The tale of two poles highlights why the southern system demands its own careful study, because what happens at the bottom of the world can ripple far beyond the ice. The link between Antarctic stratospheric warming and Australia's weather is direct and powerful, shaping the climate in ways that are both dramatic and unpredictable. When the polar vortex weakens, the westerly winds shift north, moving closer to Australia and altering our climate. This shift in wind patterns can happen rapidly, catching many by surprise. As a result, southeastern Australia often experiences clearer skies, reduced rainfall, and hotter, drier conditions. Classic signs of a post-SSW season that can last for weeks or even months. In 2019, a major SSW event primed the landscape for the devastating Black Summer bushfires by intensifying drought and heat, leaving communities vulnerable to disaster. Conversely, a strong cold vortex in 2023 kept the westerlies locked far to the south, leading to a surprisingly cool, wet summer across much of Australia, even as El Niño threatened hotter conditions. The state of the Antarctic stratosphere can override other climate drivers, keeping Australia's weather on a knife edge and making long-term forecasts especially challenging. These stratospheric shifts are a key focus for forecasters, as they can tip the balance between fire and flood and have a direct impact on communities, agriculture, and emergency planning. The lesson is clear. Remote atmospheric events can have immediate, life-changing impacts here at home, affecting everything from water supplies to daily life. Australia's climate future is inextricably tied to the frozen skies above Antarctica, reminding us that what happens at the bottom of the world can shape our lives in profound ways. SSWs don't just change temperatures, they also reshape the Antarctic ozone hole. The ozone layer, our shield against UV radiation, is most vulnerable when the stratosphere is extremely cold. SSWs warm the stratosphere, preventing the formation of polar stratospheric clouds that drive ozone destruction. Major SSWs, like those in 2002 and 2019, led to smaller, shorter-lived ozone holes. When the vortex breaks down, ozone-rich air from lower latitudes can mix in, helping to heal the hole faster. But changes in ozone also feed back into climate, affecting temperatures and wind patterns. The interplay between ozone and SSWs adds another layer of complexity to southern hemisphere weather. It's a vivid example of how one atmospheric shift can trigger a cascade of effects across the planet. For years, scientists thought major SSWs in the south were extremely rare, maybe once every 60 years. That was based on a strict definition, a complete reversal of vortex winds. But even events that only weaken the vortex, like in 2019, can have major impacts. If we broaden the definition, SSWs may happen every 20 years or so, far more common than once believed. The current 2025 event, with its record heat spike, shows these disruptions are a recurring part of our climate system. Scientists are now refining how they detect and classify SSWs to improve long-range forecasts. Better understanding their frequency means better warnings for communities facing hotter, drier, and more fire-prone seasons. The 35-degree stratospheric heat surge over Antarctica is more than a meteorological oddity. It's a warning for millions. For southeastern Australia, it signals a heightened risk of heat, drought, and fire, echoing the Black Summer of 2019 to 20. These events reveal how deeply interconnected our climate is, with changes in the polar stratosphere rippling across continents. They also challenge our models, pushing scientists to improve forecasts and understand how climate change might alter these patterns. Some research suggests SSWs could become even rarer in a warming world, with unpredictable consequences. The lesson: our fate is tied to the health of the entire planetary system, from the outback to Antarctica. The more we understand these connections, the better we can prepare for the challenges ahead.